Hello, and thank you for joining us today. On behalf of Friendship Systems, I would like to welcome you to today's webinar about CAD modeling of turbomachines, specifically to talk about the recently added functionality for this purpose in CAESES version 5.2. Let me introduce myself. My name is Matthias Brenner. I am responsible for sales and marketing here at Friendship Systems. I've been with Friendship Systems for about 16 years now, and I've previously worked in pre-sales and engineering. I'm originally a naval architect, but over the last few years, I've spent most of my time dealing with turbomachinery and development of our business in this field and working with our customer in this field. I'm joined today by two of my colleagues who will take care of some nice live demonstrations in this webinar. In order of appearance, we have Carsten Fütterer. Carsten is a CAE applications engineer here at Friendship Systems. He is specialized on powertrain and turbomachinery applications. He's also been here quite a while, for about 10 years, and he has a degree in process and chemical engineering. And also we have with us today Hedi Böttcher. Hedi is a support engineer and marketing manager. She is also specialized on turbomachinery applications, and she's been with Friendship Systems for about 5 years and holds a degree in engineering science. So before we actually get started talking about our content today, I would like to talk about a few housekeeping issues. Today's webinar will be recorded and then it will be made available for you for replay. So you will get an email with a link to the recording after this webinar, so you can watch it again or look up certain things at your leisure. If you have any questions that might come up throughout the webinar, you can submit them directly in the interface of the webinar, and we'll have a short Q&A session at the end, and we'll try to address as many questions as we can there, or otherwise we'll follow up with you. All right, just allow me to give a brief introduction about CAESES. I know a few of you joining us today are already well aware of what CAESES is, but there's also a few newcomers who might not have a full picture, so I would like to give a very brief introduction about what CAESES is. So first and foremost, it can be said that CAESES is a highly specialized CAD system for the design and modeling of turbomachinery, among other applications. It has a focus on the efficient modeling of any type of geometries, including the most complex geometries. Everything, more or less, in CAESES is really fully customizable for tailor-made designs and CAD models and workflows, and a special focus on our CAD environment in CAESES is the reliable or robust variant generation for design studies and optimizations. But CAESES is also an automation environment that allows you to integrate arbitrary simulation tools in the process, and it is also a comprehensive optimization platform to run design explorations and optimizations. So this is basically the summary of what I just talked about. So as you can see, the three main components of CAESES: the CAD environment on the one side, the optimization environment on the other side, and in the middle, what is called automation here is basically the interfacing to external simulation tools, which in many cases that our customers are working on are CFD codes, but it can basically be any arbitrary type of simulation that you can use to evaluate your geometry in the optimization process. So quickly, as I said, one of the main applications for CAESES is turbomachinery design, And of course, we have a set of dedicated turbomachinery design capabilities. CAESES includes a comprehensive modeling environment for blades, turbomachinery blades, and casings. You can really control the geometry in the finest detail, including details like leading edge shapes, blade tips, end wall contouring, scalloping, and so on. Apart from the, let's say, main flow path, you can also include arbitrary secondary flow structures, like, for example, bypasses, wastegates, cooling structures in a blade, as you can see in the picture. You can also, in the modeling process, consider manufacturing constraints that might be imposed on the geometry, for example, related to certain milling procedures like flank milling or casting, pullability of the geometry for casted parts. You can also work with imported geometry, import them, analyze them to extract parameter values, or also perform fitting procedures if you have a parametrized model that is suitable for the imported geometry, to fit that model to the imported one. With imported geometries, alternatively to modeling geometries from scratch in CAESES, you can also apply morphing. So we have a set of morphing functionality and tools available that allow you to do quick adjustments and also optimization of imported geometries. CAESES is not a preliminary design tool, so it doesn't come with inbuilt preliminary design capabilities, but we have a full programming and scripting environment within CAESES, so that you have the possibility to also implement your own customized preliminary design methods within the system and within the modeling process. So here, as I mentioned, we cover all kinds of geometries and models, and here you can see a couple of example applications in the turbomachinery field, like turbochargers, bladed geometries, but also volute casings, gas or steam turbines, propellers, fans and blowers, pumps, as well as hydro turbines. All right, with that being said, we want to talk about new functionality, new things that have happened in our most recent release, CAESES 5.2. And this release was really focused on turbomachinery, and we wanted to add a bunch of functionality to make life easier for turbomachinery designers that are using CAESES. And the main new functionality that we have added in CAESES 5.2 is the so-called turbomachine workflow. You can see it here highlighted in the menu ribbon for the turbomachinery functionality. And the motivation behind this so-called turbomachine workflow is to provide a step-by-step process to the user for the geometrical modeling of fully parametric turbomachinery geometry. It's aimed at supporting the designers in selecting and using machine type dependent features and functionality, but also it helps by keeping the project structure clean and organized, and it will also definitely speed up significantly, I would say, speed up the modeling process. So this is a little bit of a view of what this turbomachinery workflow entails. So basically, the content of this workflow is a large collection of components and parametrized geometries that can be created throughout the modeling process with a certain hierarchical structure. It does provide a structure to your CAD models and the modeling process, But it's important to know, even though it provides throughout the whole process different templates and prepared things, it is completely customizable at every step. And also the structure, this is maybe something more for the people with CAESES know-how. It provides also a dependency structure to more easily manage objects in your model and address components of your model, like you see here in this example, where we have a command that gives us a certain component, in this case the hub contour, from our meridional contours. So to make this a bit maybe more understandable, I would like to zoom in on part of this component structure. So let's take a look at what is happening here in this bladed component, specifically in the modeling of a blade here. So what we're looking at here is a so-called camber blade or camber-based blade. This is a definition that is mostly used for radial or centrifugal blade, and it is based on meridional contours, a camber definition, which is based on blade or wrap angle distributions, and a thickness distribution, and then basically allows you, by combining this information, to generate your blade. And if we look at an example here for a radial turbine, we can go through these steps that I mentioned. For example, starting by creating, we create a turbomachine and a bladed component here. And as a first step to create this specific blade, we define the meridional contours like hub and shroud contour, leading, trailing edge, maybe back this contour and a nose. And then in the second step, we can add the information that specifically defines the shape of the blade, like the camber definition. Here, the camber or mean camber surface of the blade is defined by a wrap angle distribution at the hub. And since we have a radial turbine, this is a radially fibered blade, so we just need the hub camber line, and then the rest of the mean camber surface is created by radially extending that camber line, and that gives us our camber surface. And then we have a thickness definition, which basically here is defined by a hub thickness distribution, a shroud thickness distribution, and the blending function that parametrizes and describes the intermediate, so to say, thickness definitions or distributions. And basically this results then by applying the thickness to the mean camber surface in our blade, and then we can finalize the whole model, of course, by adding fillets and other geometrical features. Another object that we have added in CAESES 5.2 is the so-called airfoil blade. This is mostly used, I would say, for axial blades. And basically, this object is a fully encapsulated blade definition, which is based on a 2D parametric airfoil definition. So we can select a parametric airfoil definition here from a given set of prepared definition or a user-defined definition. And then as a second component, we have a transformation from our 2D airfoil to 3D, so transforming the airfoil onto a stream surface. Here we're using, for example, a ZR theta transformation. There is also other types like MR theta and so on. And from our 2D parametric airfoil definition, we will also get a set of parameters that are used to control the airfoil shape, And here we can assign constant values for these parameters that keep this value constant in span-wise direction, or we can insert functions that allow us to vary that parameter value in radial direction. For existing CAESES users, maybe it's interesting to know that basically this object or definition encapsulates what you would previously have done by using a curve engine and a meta surface. So now basically you have just one object that takes care of everything and generates the blade surface in one go. And again, quick example to see how it looks like. So we have an axial compressor blade that we're modeling here. So again, we start by defining meridional contours like hub and shroud contour, as well as the stacking axis, which in this case is at the leading edge. And then using our airfoil blade that I just showed, we can combine our parametrized airfoil definition with radial distribution functions for these different parameters that we have defined, and then generate the blade. And finally, of course, again, finalize our model by adding fillets or end wall contouring like it was done here, and so on. So another thing that we have intensively worked on is filleting capabilities. So we have added specifically a so-called blade fillet, which is designed to be very robust in terms of variation of the geometry and ready for any type of custom implementations. You can create variable radius fillets as well as constant radius fillets. You can, for example, apply individual colorings to the suction and pressure side. And it also includes functionality to optimize the boundary of the fillet so that the fillet itself does not cross a given boundary curve. And there is also things like a section mode for debugging, where you can really look at the individual sections of the fillet and see where maybe something might go wrong, and quickly get an idea of how the fillet looks like. There's also some auxiliary functionality that we have added. One is related to also fillets. As we just talked about, there is a functionality or a command to get the maximum fillet radius between two blades, which will give you the location and the value for the maximum fillet radius, which is useful if you have constant fillets at the blade roots within a confined space. Then there is also a set of analysis features that you can use to analyze given geometries. For example, we have the turbo blade analysis as well as the section analysis, which will give you the blade angle beta and wrap angle theta distributions in meridional coordinates for either a individual blade section or for the complete blade. Other functionality to do inverse cylinder transformation to transform data from cylinder coordinates in Cartesian coordinates, or functionality to calculate the area distribution in the meridional plane, extract the mean camber surface from a BREP, for example, from an import, transformation to the meridional plane. There's also some imports that are available, like a blade gen import, a geom turbo import, turbo design import, which allow you to import data, for example, from other preliminary design tools. And a bunch of commands that are available if you're doing a bit more of in-depth work and scripting to, for example, transform or get the cylinder coordinates from a given point, and so on. There's also some new samples and tutorials available. So we have updated and added new sample models within CAESES that you can look at to have an idea of how this new functionality is used. So we have added a radial turbine, centrifugal compressor, a centrifugal pump, as well as an axial compressor. And we have also added some new tutorial videos for the Turbomachine workflow on our video channel page, watch.caeses.com. You can have a look there. All right, so much for the introduction about what has been added, what the news are. Now I would like to give the floor to my colleagues to demonstrate this functionality on some real-life examples. And first up is Carsten, who is going to show you something about a centrifugal compressor modeling. I'm gonna make you the presenter, Carsten. And
yes, hello. Thank you, Matthias. Just quickly say if you see my screen, Matthias.
Yes, it's
perfect.
visible.
Yeah, all right. Thanks for joining, and I will try to demonstrate you how to create a main blade from a compressor. It's basically based on our example file, so you can also have a look into it in depth inside CAESES. Yeah, first of all, we go to the Turbomachinery workspace, and as Matthias said, we create the design process by using the Turbomachine workflow. So I click here. We can call this, for instance, compressor, and this is our main object where we define the machine type. So here we have right now the example for compressor, turbine, pump, or fan. So right now we want to create the compressor blade. And then we create here components. So one component which we want to model now is the blade, and the blade it's a bladed component. So I click here. So I can call the bladed component my impeller. An unbladed component which we could model also is here, for instance, a unbladed diffuser section or an inlet section, for instance. So right now we are modeling the impeller, and the flow type is, in our case, centrifugal. The design type is based on a camber surface, and we can set a number of blades, which is 9. We can use 9 now, which is basically a set of blades. Here you can set the blades. So like the different blades. So we can put in here a main blade and a splitter blade, for instance, and those will be repeated 9 times. And for the base for the blade is basically the meridional contours. So I create, first of all, here a new meridional contour object. And as you can see here, first of all, we can initialize our contours with a radius. So for centrifugal type of machines, this will be the outer radius of the hub contour. So 30 is okay, and I can create now simply click here on the plus, and I have a bunch of different options to create a hub contour. Sorry. In our case, we can create, for instance, a hub contour with 4 tangent points. So this gives you an idea on how you can model your hub contour. You can easily change it here, so there's no problem. You are completely flexible. The only thing which you need to do afterwards is put in here the hub contour you want to use for your project, and that's it. So, so it's completely customizable. There's no restrictions. So, and we look in here. So we can change the outer radius here, obviously. And an axial length factor. I will make that a little smaller. So default value 0.8, and it's something like this. So they can change the axial extent. I can, when we look at the control polygon of that curve, I can change, for instance, the tangent factor here, which is the distance to that control point. Yeah, and then the next step, I go back to the meridional contours and I will create the shroud contour. This will be based on 3 points in our case. So I want to now reference the axial extension actually to my hub. So I click here the parameter and reference that to my hub extents. And the same I want to do with the outer radius. Instead of having an absolute value here, I make it a parameter and reference that to my hub contour outer radius. So now I can easily change the outer radius and both contours will follow. Yeah, and of course I have a bunch of other parameters which I could change here. For instance, the weight of the middle point. Then I would create the shroud gap contour. When I zoom in, it's an offset, and I have 2 parameters here. For instance, I could change the value here. That's it. And I need to create leading edges and trailing edges. So leading edges, I will create 2 for a main blade and splitter blade, for an example. And I want to create one with 2 intermediate points. So it's quite simple. For instance, I could change here those values. And I will do the same for a splitter. So go here, and this for splitter, I just want to have 1 value. So I go, I want it more at a higher position. So something like this for the hub, something like this for the shroud, and this, and then I create for the trailing edge just a straight line for our case. Zack, and that's it. So you can see it's quite now everything is dependent on each other and will follow. So that's quite nice. My meridional meridional contours is now basically done. I will go back to the impeller and I want to create the main blade itself. So I go here and create a new impeller blade. First thing I need to set here is the leading edge. So which of the 2 leading edges I want to use. So I want to use that leading edge. And then I create a blade camber object. And the blade camber object here, first of all, I need to say which angle distribution I want to use. In our case, I want to use a beta via M prime distribution. And then I create here an angle distribution for the hub. And I do that based on a curve with tangent control. So I can now look into my 2D view here. And filter for angle. And the first angle should be something like 50. I can put it as a design variable. Lower bound 40, upper bound 60, for instance. The second value should be 25 is fine, or I can put it 230, for instance. And the first tangent should be negative, so lower bound should be minus 60, minus 40, and the default value is minus 50. And the second should be something like this. So this should be my beta distribution for my hub. Similar thing I can do for my shroud. So I use here same curve type. But what I want to do is I want to follow it with a delta right now to make it simple and fast. So I make it the angle itself. I want to refer to my first angle. So like this, and I add another delta angle here. So I add, for instance, 10, right click on it and create a design variable. So this is my delta beta. And I will, for the simplicity, I will use the same delta for my angle 2. And tangent, I also just refer. So now you can see when I change the angle of my hub, my shroud will follow, and I can easily change here 5 to 15, for instance, my shroud angle distribution. So I have now two angles. I can, based on these and my meridional contours, I can create the hub camber line, go here and go stream camber line via stream section. So this will create now in 3D my stream section. Let me create a surface of revolution for the hub surface so that we can visualize it more easily, like this. Okay, and let hub surface, and I can do the same thing for the shroud. And for the shroud, I want to use a stream section with rake adjustment, so that will automatically put in a rake angle at the trailing edge. So you know that when I use the camber angle distribution beta, the theta at the trailing edge is undefined. So that method will basically rotate the camber line so that I have a certain rake angle, and I can change the rake angle. From those two camber lines, I can create now a camber surface. We have a different options here, and I will use the equally spaced stacking. So here I have now the camber surface. And now to show the rake angle, it's more easy to see. All right. And also I can change the hub. All right, so now I have my camber. Next thing I need to do is to create the thickness distributions. I can do it asymmetric, but in our case, I will make it symmetric. So I just click here on plus, and I need to create a hub thickness distribution and a shroud thickness distribution. I create one with 4 points. Let me here show the 4 points. Okay, so I can now just change the points so that I have a nice thickness distribution, something like this. It's reasonable. And for my shroud, I just want to create a constant thickness. So click here and change the value 2.5 millimeter, for instance. All right. And then I use the two thickness distributions and I create a blend between those. So click here and click the first thing, blend definition. Another way would also flank milling setup to create flank millable blades. But here I want to use a blend definition. So what that does is actually to blend between hub and shroud with a predefined function. So you can select that one here and you can see this is the function which is used to create the blending. I have one parameter here defined and I can change that parameter, the A parameter, from leading edge to trailing edge for each section. All right. So the thing what is now missing is the leading edge definition. So I go back to my blade, click here on edge definition, blade edge, and filter here for edge. I can also add my thickness. So what it does is actually it will fit ellipse, normalized ellipses to the leading edge and to the trailing edge. And I can go here to my edge definition and change, for instance, the ellipse factor, and that will change the shape. And you can also put in here a function. So right now it's a constant value from hub to shroud, but you can also put in a function to have a distribution from hub to shroud. All right. So that's it. The needed information to create our blade. So I go to blade surface here and just create blade from camber and thickness. And voila, we have now our blade in 3D. So now I can change, for instance, the outer radius. The blade will follow. I could change the camber angle. I can change the rake angle. And I could change, for instance, the thickness. Yeah, and that's the step to create the main blade. It's very similar to create the splitter blade. For instance, for this kind of blade, you can then go to the impeller, create another impeller blade, and follow the follow this workflow. But for now, I will keep it like this.
All right.
Thanks.
All right, great. Thank you very much for the very good demonstration. I think we saw how quickly you could create a rather complex geometry and parametrization. So now we are going to switch over to Hedi, who will show us also a demonstration of a blade modeling, but for an axial blade using the airfoil blade that we introduced before. And now, Hedi, you're free to start.
Yes, thanks a lot, Mattia. Let me share my screen here. Okay.
Perfect.
So, yeah, can you see my case screen? Okay, perfect. So, like Mattia mentioned, I would like to show you quickly in more or less 10 minutes how easy it is to set up an axial blade using the workflow that Karsten already showed for the radial blade. So the first steps are quite similar. So we start off with the Turbomachine workflow, which will guide us through this whole process. We can rename it to my axial compressor I want to design here. And then the first steps are like Karsten showed already. So we want to design a compressor in this case, which this setting has influence on my on the templates I can choose later on in the process here. So we want to create the blade for it, add a bladed component here. And instead of this centrifugal radial setting, I would like to set up an axial blade in this case. And we want to use the airfoil blade, which Mattia showed earlier in his presentation. So the airfoil blade is actually comes in quite handy and lets you create a fully parametric model based on a 2D airfoil profile definition, which we will see in a couple of minutes. So let's say we need 15 blades here. And then this part is still kind of the same that Karsten showed. So we usually go to the plus on the right side to add this object here. We also need meridional contours and can insert a reference radius here. For the axial setup, the reference radius is based on the hub radius, so my inner blade radius here. So I would like to define 150 as my radius, and then I want to add a simple axial straight hub contour. So this template kind of created all of my points and lines and also the parameters for me, and yeah, we have a simple line here, not very spectacular to look at, but already linked to the parameters here as an easy starting point for the setup. So I could maybe rename this one to hub radius. Then we have different length settings, which has an axial length factor, but in my case, I want to keep it simple and just get rid of this whole expression and just define a value of maybe 300 millimeters here. And you can adapt the objects here as you like. So I just throw out the one parameter I'm not interested in right now to clean this up a little. Okay, so if I go back to my main meridional contour object, I can see, okay, the shroud contour would be next. So I can add a shroud contour, which I will also give it a straight line, adding a shroud contour here. So the same thing with cleaning up this still simple template setup. I will just throw out this expression and reference it with the Alt button. I can reference this in cases to make it the same length as my hub axial length to keep it together. And then I don't need this parameter anymore. So what I would like to do is this radius is predefined up to a range of 270, which I would like to increase a little bit. So let's give this up to 350 millimeters and change my default value to a outer radius here of 300. So if I use my default value, I have the blade length between my hub and my shroud contour or tip contour of 300 millimeters in this case. So one only thing that is missing now to set up my airfoil blade would be we need a stacking axis. So we don't need the shroud gap here. I just defined my shroud contour, which is I want to run my blade to run from hub to shroud contour. So I don't want to define a gap in between. I need a leading edge, which can be as complex as you like. So you can either use predefined versions here with 1, 2, 3, 4 intermediate points, which we offer here. Once you pick one, it's also not a stiff setup. So if you pick one, you can always change it to a more complex setup later on as well. So this template kind of created a straight line here in the first place. But I have the possibility to shift my starting point here along my hub contour, for example, kind of similar to the setup we've seen in the centrifugal case. So I can shift it along my line, which is a simple line here in this case, but can get as complex as you like. I can do the same as for the position on the shroud here on the top line. So move this along. And what's also interesting to see here, we can rotate these points also in around the z-axis, so around our rotation axis. So we can kind of give these values here theta and kind of move the stacking axis here out of that one plane to give it kind of a wavy shape, if you like, or whatever shape you can imagine or fit into your optimizer. Anything is possible here. And also you could insert an inclination of the entire leading edge stacking axis here. So that is pretty much all we need to define our blade. Let's create for the hub contour. I usually like to create a surface of revolution to make this a bit nicer to see. So I can create a curve-based surface of revolution here. So as my hub surface, and then we have created all of the necessary parts here in this setup, in the meridional contour setup. So I can go back to my bladed component here and add an actual blade here. This is the airfoil type. That's the type of blade I want to use. So I could use this airfoil blade here. Like Matthias showed in his presentation earlier, the airfoil blade is made up by 2D profile definitions. So we have some predefined profile definitions here, which define the profile parameters in 2D, and which are then used to sweep between hub and shroud, or to like loft the surface between hub and shroud. So we have some different predefined definitions here, but you could also use your own definition as you like. We have different setups here which are normalized or absolute, which refers to how the thickness is defined. So you can either define the thickness in like absolute millimeter values, or you can use the normalized setup and reference the thickness to, or define the thickness values relative to the chord length. So like in percentage of chord length. So let's use the first profile definition here. And then what we can see is this is the normalized definition, and my blade is 1 dimension, 1 millimeter long. So I need to scale it. I have here the chord scaling, so it's now 1 long. So let's scale this to a longer blade to be like 138 millimeters in our case. And yeah, we can see like in about 10 minutes, we set up a axial blade here with the predefined workflow and different definitions here. You could adapt to your needs as well. And we have some predefined settings here you can choose from. So right now we have the leading edge stacking, which is here, yeah, my blade is stacked here at leading edge, but you could also choose and stack it in the center of area here. So kind of shifted with this setting. And you have some predefined parameter values here, which the ones here at the bottom come out of my feature definition, which we looked at here in the beginning, or which we chose here on the top. And some of the transformations are already predefined here. So if I want to add a stagger angle, I can do so. And these don't necessarily need to be constant values. So Mattia also mentioned it in the beginning. You could also insert functions here and then kind of change the profile sections along radial with the radial functions, and you don't need to use constant values. Yeah, maybe just one more quick look into this 2D definition of our profile. So if we look here, this is a feature definition. So as soon as I add it here to my airfoil blade, it should also appear in my feature definition area here. So if I create this feature, I get a test section. So I can take a look at the profile definition and see here in 2D what my profile looks like. That is then used to sweep here along the leading edge stacking axis. So if you want to write your own profile definition, you just need to define it here in 2D space in the X and Y plane, and can use your own profile definition to feed into the airfoil blade and use it for the surface creation. Yes, so one last small thing, maybe we could create here some periodic images, and then we have also seen in the beginning that we can extract some information here from those components as well. So I can get the number of blades here from what we defined in the beginning, and then have a full setup here. This for visualization, at least here in this case, of our compressors data with the airfoil blade and the Turbomachine workflow. All right.
Yeah.
That's it from my side. Thank you.
Excellent. Thank you very much, Heidi, for this impressive demonstration. I think it's amazing, especially if you're a long-time CAESES user like me and maybe some of our attendees, how quickly you can generate these kind of geometries now with this new workflow, which in the past would have taken much more effort, like, as I said before, meta surfaces, curve engines. You don't need to define the transformations as part of your section features anymore. So it's really makes things easier and faster. So we're going to give back to Carsten now for a final demonstration on the new filleting capabilities. So let me switch to you, Carsten.
Yes, thank you. Maybe we extend 4 or 5 minutes or something like this today, but hopefully it's fine. You can leave earlier. You have a recording. Everything is fine. So yeah, let me demonstrate you the new fillet functionality. We have actually rewritten the whole code now by ourselves, so that we have a really tailor-made or custom implementation, and we are now really like if the fillet is not working, we really can debug it, and we really can also solve the problems, and we can make it customizable and add different kind of features. So yeah, let me demonstrate it first. So I have prepared here something. You can see this is a turbine blade. It's also found in the examples. So we have a segment already, which was created, with the marine contours and the blade and so on. We have from the hub solid, we have created a segment by defining those boundary curves here, the blue ones. Created the boundary surface and trimmed the hub into one segment. Then I have also prepared the blade, so I need also a closed blade, which is intersecting with the hub. So this is already done. Okay, so now we can create. We have also scallops here. Now we can create the fillet. So I create a new scope, say 0 fillet, and therefore I go now again to the turbo workspace and create a blade fillet. The fillet is really dedicated for blades. So here I put in first of all the hub BWrap. So this is my scallops. Then I put in my blade BWrap, which is my closed blade. Now here comes this like kind of special thing. What it does is actually it's just doing a Boolean operation between hub and blade. And at the beginning, it does not know, the code does not know where the leading edge is, where the trailing edge is, where is side 1, where is side 2. And we have to give a little more information. And we do this with reference surfaces. And the reference surfaces just define one side of the blade. So when you have created the blade with the workflow you already have, created automatically one side, like both sides as separate surfaces. You can see side 1 is, goes from leading edge to trailing edge. It's also a little bit extended. So we need to provide this surface in order to clearly define leading edge and trailing edge. So I put now here this list, this surface. It can also be a list of different surfaces. Now we can decide if you want to have a constant radius or variable radius. Of course, we want a variable radius because it's much cooler. So I can give fillets for both sides, for instance, fillet boundary and another. And why is it not working? Okay, of course, we have to provide the radius functions. So I go to CAD, I create a NURBS curve, simple NURBS curve with a planar B-spline curve with 6 control points is fine. I call this one fillet function side 1. Function. So I can now change points. To some value. Something like this could work. I copy that and I have a same for my second side, make it maybe a little bit smaller. So I can now put in those 2 curves into my fillet BWrap, fillet feature. Now it's updating, and you can see it has created the variable fillet. It also nicely goes around the leading edge fillets here from the hub quite nicely. It has clearly separated boundaries for side 1 and side 2. And I can change now easily the fillet values by dragging the points. Now, when I would have a too large radius, which would interfere with the boundary here, usually the fillet would break, but we can avoid that because we can add here active boundary optimization, and we can insert boundary curves. The boundary curves will be inside the algorithm, will be used to restrict the radius of the fillet sections at that position. So when I look at my segment, I have the 2 boundary curves. I take this one and I take the other one. Of course, right now there's no difference, but when I increase the radius of these and what you can see here is the fillet was actually restricted and in that area. And what I just did is I can also set a certain distance to that boundary. So of course, a distance of 0 would be really difficult, but you can put in a small distance here, and then those sections are automatically optimized. And we can, which is also nice, look at the section preview. So that gives us an indication of the radius of the sections itself, which are optimized. And we can also access the fillet functions. So okay. Now you can see it has actually reduced our initial radius function with that value. Yeah, that's it. I could also show you the maximum fillet, but right now I think we are over time, and I will keep it like this. Yeah, thank you.
Very good. Thanks, thanks, Carsten, again for this other demonstration. So yeah, as you said, we're slightly over time, but we can still pick up a few questions here for people who want to stay on. I've got a question here, which I think raises a very good point, and if it hasn't become clear, that's definitely something we need to clear up. So the question is related to, or I'll just read it out. It used to be that CAESES feature definitions could be modified or customized as the user needs them. It seems like the objects now do not show the feature definition editor button. Is it not longer possible to customize by the user, or is it possible to build up similar functionality as customizable? So I think it's important to note here that, yes, here in these demonstrations, to speed up the whole demonstration and not overcomplicate things, we've used, or Carsten and Hedi have used a lot of predefined definitions. So for example, for, I don't know, meridional contours, for 2D airfoil and so on. So at every one of these points, in the process, we provide, so to say, a library of predefined definitions. But first of all, you can modify these definitions because they will just create a bunch of objects like a curve with points and design variables. So you can either use these templates and then modify them to your liking, or you can also define completely custom definitions. So if you don't want to use a meridional contour or an airfoil definition that you see there in the list in the given library, you can just simply use your own one, and you can use feature definitions to write your own airfoil definitions and so on. So every step in this process and everywhere where you create a certain definition for a component of the process, everything is completely customizable as it was before. It's just that this workflow provides kind of an overall structure where you have a certain process, so to say. The process, yes, is in some way predefined if you want to use it like that, but you can customize it anywhere throughout. So that doesn't really change from before. Then we have maybe some other question. How to transfer the 2D blade to 3D blade. So I'm not exactly sure I understand this correctly, but my assumption here is that maybe the 2D section of the blade, how to transform that to 3D. And this is basically what is done by the airfoil blade, which takes a 2D cross-section of the blade as an input, so a 2D airfoil section, which is parametrized, and then it wasn't really discussed in a lot of detail, but you have different methods that you can use to transform your 2D definition into 3D. The easiest one is to simply transform it to use a cylinder transformation, which basically transforms it onto a cylinder with a given radius. And then there is other transformations like the one that was used by Hedi in the example, which is the ZR theta, or there is also MR theta, which are different transformations methods like angle or shape preserving that are used to transform the 2D section onto a 3D stream surface, which is basically located between hub and shroud. So we had a very simple example here with the cylindrical hub and shroud, but in a, let's say, more complex turbo machine, you might have curved hub and shroud contours, so you have also more complex shapes of your stream surfaces onto which you will transform the cross sections. So this is basically handled by that transformation part in the airfoil blade definition. Again, this can also be done in a customized way. There is a question here about the analysis of existing geometry, which we haven't showed in any demonstration here. There is a question whether there is examples for that in any tutorials. I don't think so, but I think that functionality is also relatively easy to use. So I think for the person who asked the question, we can definitely get back to you and show you how things work if necessary. So. Another question here is related to can you have a fully integrated entrance, I guess leading edge and thickness distribution all in one 2D section for radial runners? I think maybe Carsten, you can add to this, or Heidi. So I guess this is related to what we've shown here for thickness distributions. So I think in the approach that you showed, you have you used thickness distributions on hub and shroud and the blending that did not include the leading edge and trailing edge, but they were added separately as edge definitions. And I guess the question here is whether you can have a basically thickness distribution which includes the leading and trailing edge as well.
Yes, sure, you could do that, and you could create your own 2D sections, and then you just put in the list of curves in the edge definition, and then it will be used by the blade itself. This would be one way. Just to another way, which might be not obviously, but you could also use an airfoil blade for purely radial blades. Just so you could also define completely the definition, the profile, and then just use that as a radial blade. Yeah, with an airfoil blade. That's also possible.
Yeah, that's a good point, Carsten. I mean, we mentioned that the airfoil blade is mostly used for axial blades, and the camber thickness-based approach is mostly used for radial or centrifugal blades, but it's not a hard limitation. You can use those approaches also for other kinds of blades. So that's a good point. There is one question. One final question, which I'm not exactly sure how to answer, which is related to the automation. Can we automate an end-to-end design process? If not, which percentage of the process can be automated? I'm not exactly sure in which direction this question is aimed. I mean, sure, you can automate a lot of things by, for example, scripting. You can, I don't know, provide maybe some input parameters and then run through an automated script to create a geometry. I don't know if this answers the question. Otherwise, maybe we can follow up on this and discuss in more detail what the specific requirements are there. I think this is it for the questions we got here right now. As you know, we are already over time, so I would come to an end now of this webinar. Sorry. Here I wanted to switch. So if any of you is not a CAESES user yet, and you are interested by what you saw here and you would like to try it by yourself, you saw there is some samples and tutorials available to guide you through the process, then you can download CAESES from our website and register for a trial license. You can, of course, also contact us if you have more questions or if you would like to discuss in more detail. And, of course, you can watch out for more webinars that will come in the future if you want to see more content like this. So, thank you very much for joining us today. Thank you for the additional time for the people that are still on here. And yeah, we hope to see you next time or to hear from you. Bye-bye.